Well, welcome back to Chapter 3. We're going to look at the empirical rule, the 68, 95, 99.7 rule. When we're dealing with a symmetric distribution, a standard normal distribution, we can determine the proportion of the variable values within a specific number of standard deviations from the mean. Or we could also call that a percentage or a probability. Now again, it has to be that we're dealing with a distribution that is approximately bell-shaped, or these normal distributions. So what does that mean? That within one standard deviation from the mean, 68% of our data will lie. Within two standard deviations, 95% of our data will lie. And within three standard deviations, almost all my data will lie within three standard deviations of the mean. So let's take a look at what that means. Let's look at the picture. Well, there's 68% of our data lies within one standard deviation from the mean. So let's say that we have a mean of 10 and a standard deviation of 2. So our mean is 10. What would be one standard deviation from the mean in that distribution where I have a mean of 10 and a standard deviation of 2? Well, being one standard deviation to the right, or a positive one standard deviation to the right of the mean, would be 12. Being two standard deviations from the mean would be at 14, and three standard deviations to the right of the mean would be 16. Now we can also talk about being to the left of the mean or smaller than the mean. Now, can standard deviation ever be negative? I hope everybody said no. Standard deviation, by its calculation, cannot be negative. Standard deviation is always a positive number. When you see this negative, but you're looking at there going, but I see negative, that negative weird symbol, for standard deviation. That just means that we're going to the left of the mean by so many standard deviations. So, going to the left, one standard deviation would be negative 2 units from the mean. So, being one standard deviation to the left of the mean would be at 8. Being two standard deviations to the left of the mean is 6. And being three standard deviations to the left of the mean is 4. So we now have, we could take this example of a specific distribution and now actually show on the number line where the mean is, where plus or minus 1 standard deviation is. Plus or minus 1 standard deviation is between 8 and 12. So I would say between 8 and 12, 68% of my data will take on values between 8 and 12. 95% of my data can take on values between 6 and 14, and about 99.7%, or the proportion of my data, will take on values between 4 and 16, or 3 standard deviations from the mean. So that's what we mean by that. Now you're looking at there and saying, well, we're getting this 34%. Where are all these little numbers coming from? Well, if being within one standard deviation from the mean, 68% of my data lie, and we have a symmetric distribution, then that means half of the data from the mean, to positive 1 standard deviation, that would be 34% of my data would lie between the mean and positive 1 standard deviation. And because it's symmetric, it means that 34% of my data will lie between the mean and negative 1 standard deviations from the mean. Now, where did the 13.5% come from? Well, there's different ways to look at that. You could say, well, 95% of my data lie between 2 standard deviations from the mean. Take half of that, which would be 47.5% of my data would lie between the mean and positive 2 standard deviations from the mean. So if I want to find that little chunk between 1 standard deviation and 2 standard deviations, I would take the 47.5, the percentage that could be from mean to the 2 standard deviation, and subtract off that 34% that is between mu and 1 standard deviation, leaving us 13.5%. So we could do that for each of those little intervals. So if I asked you, what proportion of my data, or what percent of my data would lie greater than 3 standard deviations from the mean, you would say 0.15%. very small percentage of data would lie greater than 3 standard deviations from the mean. So do you think it's very probable that a data value will take on a value in our specific distribution? Remember we said 16. Do you think in our example that any data values that the likelihood of a data value taking on the value of 18, do you think that's very likely? And hopefully you'd say no. It's probably not going to happen. But if I could say that a data value taken on, if a data value took on the value of 9, you'd say, yeah, that could happen for sure. So that's what I hope that you'll see, that what this empirical rule gives us, and what, when we look at a standard normal distribution, what the standard normal distribution gives us. Now, on the next slide is the way in which we can compute these with what I just did. So it gives you a little bit of extra to look at. Well, here we have a great discussion for our blackboard. Tell me what you think about this. Now, knowing the mean and standard deviation, it can help us. We can actually have a good idea of what's going on with that normal distribution. With larger standard deviations, our normal distribution will be spread out a lot more, because that means the standard deviation is larger. So it will be lower and spread out. If our standard deviation is small, our normal distribution looks very spiky, peaks up very high in the center, because we have to still remain the same area underneath the curve. So my example here is always, if somebody has a little bit of extra weight and they put on pants that are a little bit too tight, what's going to happen? You can't get rid of the mass there. It's got to go somewhere. It goes up and out. So that's the kind of idea of squeezing all that data in the middle part. But if you wear a pair of jeans that fit you better, everything relaxes. And yeah, there's a little bit more of a spread out, but there's nothing that just spikes up in the middle. Now, let's go look and see what happens if we had the same standard deviation but different means. Well, look what happens to our distribution. It just shifts along the x-axis. That's all. So with different means but the same standard deviations, we have two distributions that look almost identical, just shifted along the x-axis. Now here's a look at if we had the same mean but different standard deviations. Our spread is different. Again, as we see, the smaller the spread, the peakier it gets, and the larger the spread, the more flat out our distribution looks. It's time to look at some properties of the normal density curve. The curve is symmetric about the mean. So that means the mean, median, and mode, the mode being the data value that occurs most often, they're going to be the same. So the highest point of that curve is when x equals mu, when your variable would equal mu. The curve has inflection points at mu minus sigma and mu plus sigma. We already talked about what inflection points were in a couple of slides ago. The total area under the curve is equal to 1. That makes it a density curve. The area to the left of the mean is equal to the area to the right. It's symmetric. So 50% of my data lies to the right of the mean, and 50% of my data lies to the left of the mean. As x gets larger and larger, now the graph never ever touches the horizontal axis. It gets closer and closer to it. It's called asymptotic behavior. The empirical rule is true for normal distributions because a normal distribution is symmetric and bell-shaped. Now, as we talked about earlier, when we collect data, we can make histograms, and for each sample, you're going to have a little bit of a different histogram. And also, histograms are based on the classes that we use, so there can always be grouping problems or errors. So it's difficult to get detailed information or calculations. So instead of using this histogram, that's why we like to model and use a probability density function that is an approximation to that histogram. So if our histogram looks bell-shaped, we're going to approximate that bell-shaped histogram with normal curves, and we can get a lot of good information when we do that.